Alright, this is a re-recording of one of our Chapter 8 lecture videos that for some reason had the audio cut off, and with repeated attempts I was unsuccessful to correct this error in the original recording, so I decided to re-record it in the hopes that the example demonstrated in it will be very useful for you to work on the homework assignment, and especially to help you prepare for the upcoming exam. And in particular, the example that I have selected to demonstrate in here is taken from our textbook, section 8.1, number 19. And in this problem, we are given the parameters, that is the population mean and the population standard deviation. So here we have the length of human pregnancies, which is approximately normally distributed with a mean value of 266 and a standard deviation of 16 days. The first question that we need to address is to compute the probability that a randomly selected pregnancy will last less than 260 days. So in this question here, we are talking about a single observed value that has a probability which lasts less than 260 days. We need to translate this into a probability equation, and we write it as follows. So we'll have a so here problem number 19, and the information given to us is as follows. We have the mean value, which is 266, and a standard deviation of 16, and most importantly, we know that the population is normally distributed. Okay. So the translation of the first question is as follows. We want to compute the probability that a mean value of less than 260 days. Okay, so we want to compute that probability, and this is what we call a representation of a general distribution. What we need to do is convert that general distribution into the standard normal distribution by using what we call the z-score, or we will now call the standard error equation, and it has the following expression. We have z equals x bar minus mu divided by the standard deviation divided by a square root of n. Now in this particular problem, we know, as I mentioned earlier, that n is 1 because we are talking about a single observed value. So what that means is that we have a 260. 260 is from here, and then minus 266, that is the mean value, which is here, divided by 16 divided by a square root of 1, and that gives us basically 260 minus 266 divided by 16. And I think I have a calculator here that I like to demonstrate. So here let's compute that. So we have 260 minus 266 divided by square root of, divided by 16, and the square root of 1 is actually 1, so we just ignore that, and this is the answer right here. We're going to round this. This is the z value, and we are going to round it off to 2 decimal places. So this will read a negative 0.38. That's what I'm going to use. And in fact, we will use this table right here, but before doing that, I'd like to, actually there are two of them, I don't know why, but anyway, so here we have a negative 3.8 for the z value, and therefore the translation of the general distribution, which is p of x bar less than 260, is now rewritten in the z expression as a negative less than or equal to a negative 0.38. Now, to confirm this, that the translation is correct, we can also check this out by drawing the general curve right here. So the general curve here has a mean value of 266. And we want to compute the probability under the area that is less than 260. So you see here, one standard deviation is 16. So that's one standard deviation right here. So that is basically plus 16 more. So you go to this side here, you subtract one standard deviation. So you take 266 and subtract 16 from it, you will get 250. Okay. So according to this expression, we are looking at a region of 260. So if this is 250 and if 266, then halfway between them, right? Right here, somewhere around here, that is 260. This is the region that we are interested in computing. The shaded region is what we are after. Now, after the translation using this z equation, we arrive at what we call a standard normal curve, which is also a bell-shaped curve. And so the standard normal curve has a mean value of 0 in the middle. That's why it's called a standard. It's 0. This is a general because it could be anything. In this particular distribution, in this particular problem, we have a mean value of 266. But in any other problems, it may have a different mean value. That's why it is general. So for this one here, you can see here to the right of it is a +1, to the left it is a -1, right? In negative 0.38, which is a roughly negative 0.4, close to halfway between it. So it's going to be somewhere around here. And this is the region that we are interested in computing in that standard normal curve. So the region in the standard normal curve and the region in the general normal curve is quite similar. So we know that we are on the right track. Now we need to look up a z-value table to find out the shaded region and what it is going to equal to. And for that, we'll turn to the normal curve distribution right here, and a negative 0.38. So you go up here, you can see a 0.08 is second on the right side, second column to the last one, and a negative 3.8 is somewhere here. So here we have negative 3 and negative 3.8 is, where's my hand is waving at, is a 0.3520. That is the answer. So the region inside this, under this curve, is equal to 0.352, and that is our answer right there. Okay. What about part B? Let's look at question B. Question B asks us the following. It says, suppose a random sample of 20 pregnancies is obtained. Describe the sampling distribution of the sample mean length of human pregnancy. So here we want to describe the properties of the sampling distribution of human pregnancies. And to answer that question, we are going to write down the following properties. So this is part B. We know that the mean of the sample mean will ultimately equal to the true population mean. The standard deviation of the sample mean is equal to the standard deviation of the population divided by square root of n. Now here in this problem, we know that n is given to us to be 20. And originally the problem also gave us that the mean value is 266. The standard deviation of the population is 16. Therefore, the answer to this question is that the mean value of the sampling distribution is also 266. The standard deviation of the sample distribution is 16 divided by square root of 20. And square root of 20 is, so here we have let's clear this first. Okay, so we basically have the negative, well, let me show you the negative number of, in other words, we have the, not the negative, the 16 radical 20, and that gives us a, oops, so instead of, okay, I'll just use this one here. So here we have a 16 divided by square root, oh, that's wrong, that is wrong, 16 divided by square root of 20. That's not a square root. Let's delete all of that. So we have 16 divided by square root of 20. That will give us a 3.578, or we can round that off to two decimal places, and that will give us a 3.58. That is the answer for the standard deviation sample distribution. So we'll go back to here and we'll just record that number, which is a 3.58. Now, so these are the properties of the sampling distribution of human pregnancy. Now, question C basically asks us to compute the probability for a random sample of 20 pregnancy. So in this particular case, part A and part C are quite similar. The only difference is that instead of n equals 1 for part A, we have n equals 20 for part C. So you need to make sure that you understand this, because it looks almost identical with part A, but with the only difference with n equals 20. So you cannot really take the answer from part A to answer for part C. That would be wrong. What we need to do then is to compute the z value for the case of n equals 20. And what that means is that we are going to, I'm going to squeeze in part C right in here instead. Okay, so I'm going to put part C right in here. So part C, we have what is the probability of x bar less than 220 for a sample of 20. I mean 260 for a sample of n equals 20. And we need to find z, and in this case here z is x bar minus mu over standard deviation divided by square root of n, and that gives us 260 minus 266 divided by 16 over square root of 20. And to save some time here, I'll just report the computed answer, the numerical answer for this one. Basically, this number is going to give us a negative 1.6. In fact, here, let me just show you, so that I was gonna just give you the answer, but let me just show you instead. So here we have so we have x bar, right, minus the mean value, which is 266, quantity divided by 16 divided by a square root of 20. Okay, so I'm going to try to do this to show you. And so you can see here we have a negative number, and we are going to report to 2 decimal places. So what that means is we're going to round this up. So here I will have a negative 1.68. Okay, so negative 1.68 is the answer. I was going to write that down, but I just wanted to show you now. So here we're negative 1.68. So now this expression is now translated to the p, which is z is less than equals to a negative 1.68. And this is basically a curve that looks like this. Okay, we have a plus 1 here, negative 1 here, negative 2, negative 3. So negative 1.68 is somewhere around here, and this is the region that we are after. So it's a pretty small region, you know, very small, you know, less than 6% or so. It's very, very small right here. So it will probably get about 6% or so. But let's compute that, and we're going to do that using the standard normal curve, which is this one right here. So at negative 1.68, and you know that the second to the last column is 0.08. The last one is 0.09. So therefore you have a negative 1.68, which is this column right here. And there you go. You have a 0.0465. 0.0465. See that? Right there. That's the answer. So the answer is 0.0465. Just as we suspected, it's less than 5%. So that's the answer. Okay, now let's move on to part D. Part D is that you look at the problem. We want to compute the probability of randomly selected sample of 50 pregnancies. So here D and C are similar, very similar. You see that the problem is the same, 260 or less, 260 or less. The only thing different is that the sample size has changed from 20 to 50. So again, we follow the same format of problem C to try to find a probability for part D. And this is how we're going to do it. Okay, so let me write this down very quickly. So part D, we have n equals 50, and we're going to compute the z value right away, which is 260 minus 266 divided by 16 over square root of 50. Okay, and you can confirm this, and the value that we found is negative 2.65. Okay, in fact you can do it right here, because also I just wanted to show you the trick how to use your calculator. You see here we have the same format, except the value under the radical, instead of 20 we're going to change it to 50. So here I'm going to use the entry that I used, that the previous equation, and I just access it by using the shift and then entry, and there's the answer there. So I'm going to change 20 to 50 right there. Now hit enter key, and that's what I got. See that? A negative 2.65, just like the answer that I just showed us right here. Oops, the wrong one. Right here. Okay, so now what we have is we'll have the probability of z less than or equal to a negative 2.65, and let's draw the curve. So the curve looks like this, a -1, a -2, a -3, a -2.65 somewhere around here. So there's a -2 right here, -0.5, 0.65 somewhere around here. This is the region that we are, the shaded region is what we're after. Okay, it's a very tiny curve. So we say that it's very much less than 5%. Much less. Well, let's do that by looking up the table. So a -2.65 right here, see that? So that's 0, that's a 1, that's a 2, that's a 3, that's a 4, that's a 5. And we want to confirm this to extend it. That's a 6, 7, 8, and 9. So this is a 5 right here. So we have a -2.65, and that value is 0.0040. Okay, that's the answer. So we have a 0.00040. As we said earlier, this is less than 0.5%. Very small. That's the answer. Okay, now let's look at part E. Part E, it asks us, what might you conclude if a random sample of 50 pregnancy resulted in a mean gestation period of 260 days or less? Well, we want the question is asking us to interpret the result we found in part D. That's what we're trying to do. Well, if you remember back in chapter 5, we talked about the unusual event. Any probability that is 0.05 or less would be regarded as the unusual event. Okay, so back to chapter 5. So let's write E here. So back in chapter 5, if you remember, we set our probability range from a 0 to a 1. 1 is a probability that will happen with certain. 0 is a probability that event will not happen, that is an impossible event. And this is a 50-50 chance, or likely. This is very likely, this is unlikely. Okay, and so this is a 0.25, this is a 0.75, and there's a 0.05 right here. Any event that has a probability of 0.05 or less will be regarded as an unusual event, and therefore we can say that in this problem right here, we can say that as obtained in part D, we can conclude that the probability of finding a mean gestation period of 0.0040 is an unusual probability or an unusual event. That's what we can say. So now let's move on to part F. And before we talk about part F, I would like to remind you to report back to me that you have watched this video. This is our video code right here, which is 0.0040. That is our video code. Now let's look at part F. Part F is a very important part to look at. Okay, so let me show you that with complete detail. Part F. Part F, we are basically looking at computing a probability that ranges within 10 days of the mean value. So basically what we want to compute, so for n equals 15, and that we want to compute the value that is 10 days within the mean value. So here you have 266 minus 10, that is going to be 256. 266 plus 10 is 276. So 76. So basically what we are trying to compute is something like this. Okay, so this is the general distribution. In other words, if you remember what we looked at earlier with the general curve, so this is 266, So 276 is somewhere around here, and 256 is somewhere around here. So this is the region that we are interested in finding. Okay, that's a 276, and that's a 256. Okay, so we want to translate this into the z curve. So in other words, we want to translate this into what z here will be, and then what z here will be. Okay, in other words, we are looking at a region similar to this. So we'll find out what this z value here, let's call it z2, and this is z1. Okay, and for that we turn to the z-score. So I'm going to start a new sheet, a new fresh sheet, and so let me rewrite this one more time. So we have a 256 and a 276. Okay, so a z1 corresponds to an x bar 1 minus mu all over sigma square root of n. In this case here you have a 256 minus 266 divided by 16 over square root of 15. And you can check this answer for yourself, which is going to be a negative 2.42, and a z2 which corresponds to a 276 of the x bar. We have here 276 minus 266 over 16 square root of 15, and that's going to give us 2.42. So these two values, the z1 and the z2 values, now correspond to this probability expression. We're having negative 2.4 z and a positive 2.4. Oops, that's not a 4. So now we're ready to compute this, and this basically corresponds to this curve right here, the general curve. So I have a positive 1, a negative 1, a negative 2, a positive 2, a negative 3, a positive 3. So what we have then is a 2.4 somewhere around here, and then I mean that's a negative 2.4. This is a positive 2.4 somewhere around here. So this is a region that we are. Now my curve is not quite steep like what I drew before, so it looks a little bit different than what I shown earlier, but nonetheless you have similar shaded region, similar area to determine. So what we need to do then is we need to break this down. Okay, you see the table that is in the book, in the back of the book, the z table, allows us to read a number from negative infinity, this is negative infinity, all the way to a certain value. So we cannot really use our z table in the book to do it, because this is a region that we try to exclude. So what we need to do then is I'm going to split these into two regions. Okay, so I'm going to split it by writing it like this: p of z less than 2.4 minus p of z less than a negative 2.42. So to draw the curve here, I'll show you. Basically you read anything all the way from negative infinity to a 2.4, so the entire region, the entire shaded region. Okay, this is what that is, and then minus this one, which is from negative infinity. Again, my curve is a little bit off. I'm going to fix it. Let's see if I can fix it. Still off. Alright, I'm going to just use it as is, and this is where it is, a negative 2.4. so this is the region. So I'm going to use my z table, read from negative infinity all the way to a 2.42, and then minus a value from negative infinity to a negative 2.42. So I'm going to start a new sheet here because I run out of room. So what we have then is, I'm going to just do it like this. So we have a P of Z less than 2.42 minus P of Z less than negative 2.42. Now let's look at our table. Let's look at the negative 2.42 first, right here. A negative 2.42, this is 0, this is a 1, this is a 2, right? So a negative 2.42 is right here, 0.0078. See my hand right there waving at that number, 0.0078. That's the second value for my curve. So here is what I have, 0.0078. What about a positive 2.42? Well, we're going to go to the positive region. So it's going to be still under this column, but I go to the plus. Go down here. So this is a 2.42 right here. That gives us a 0.9922. 0.9922. Okay, so here we have a 0.9922, and the difference, if you take the difference here, you can see the difference is quite is still quite big. You're minusing a very small number, so the answer is 0.98. 7, so 82, that's a 4, and 871 is 8, so it's 44. And that looks about right, because you see here what we had drawn earlier is that this is the entire curve right here that we are interested in finding. So this answer pretty much tells what the region is. The shaded region is about 98%. And that is the answer. Okay? Well, thank you, and good luck on your exam.